Okay, so today we will continue our discussion of reactions of monosaccharides. We'll talk about a couple of processes, the Bohl degradation, which enables us to chop one carbon off of the chain of a monosaccharide, the Kiliani-Fisher synthesis, which allows us to add a carbon to the chain of a monosaccharide. And then we'll conclude with the discussion of how Emil Fischer, one of the greatest organic chemists of all time, was able to determine the structure of glucose. He did this back in 1890, well before any spectroscopy. His only analytical tools were a melting point apparatus and a polarimeter. So to be able to determine glucose's structure with those tools is a remarkable achievement, and we'll talk about how he did that. But first, we'll talk about some more reactions. We left off on Monday mentioning that if you expose a monosaccharide to strong base, you will isomerize it. We showed you how you can convert glucose into a mixture of glucose, mannose, and fructose. And we said that what that does is it prevents us from using the Williamson etherification reaction for making ethers from monosaccharides. So if we want to make ethers, we have to use a different reaction. And that reaction is shown here on the board. We can use silver oxide and iodomethane. Obviously, we're using an excess of the iodomethane. We're making ethers of all the OH groups. We can react the anomeric carbon. We can convert the hemiacetal into an acetal or a glycoside. Right? We learned how to do that with HCl and methanol, but we can also convert all the other alcohols into ethers using silver oxide and iodomethane. So the book doesn't draw a mechanism for this, but the book gives you a description, a brief description. In its attempts to simplify things, it actually makes some inaccurate statements. Okay? So instead of relying on what's in the book, we're going to actually draw the mechanism of this etherification reaction. The book says that silver oxide is basic and can deprotonate alcohols. That's partially true. Silver oxide is basic. When you dissolve it in water, you do get a basic solution. But it is not basic enough to deprotonate alcohols. If it was, it would be basic enough to make enolates, and we would get that mixture of isomers that we showed you on Monday. So it cannot be basic enough to deprotonate alcohols. But in addition to being basic when it dissolves in water, it's also a good Lewis acid. Silver, having very low electronegativity, like all metals, is going to have a very polar bonds to oxygen. And so these silvers are going to have pretty substantial partial positive charges on them. So when our silver oxide interacts with our iodomethane, we're going to get a Lewis acid, Lewis base complex, similar to the sorts of complexes we saw in electrophilic aromatic substitution. Friedel-Crafts reactions, halogenation reactions. We saw complexes of this nature. Okay? So by coordinating one of the lone pairs on the iodine to our Lewis acid, we make that iodine an even better leaving group. And so that allows a weak nucleophile, such as an alcohol, to attack that methyl group. A weak nucleophile, such as an alcohol, will not participate in a normal SN2 reaction. But if you soup up the leaving group ability of the iodine by coordinating it to a Lewis acid, now our weakly nucleophilic alcohol is able to attack that methyl group. Okay? We're not going to draw the crazy-looking leaving group we get from this, but we're just going to go ahead and draw what results. Okay, is this species here, the conjugate acid of that ether, and then we'll have a base. We're not going to specifically identify the base. We'll just draw it as a B. Suffice it to say that silver oxide dissolved in water does give you a basic species, and that enables us to obtain the desired ether. Okay? And of course, we have the conjugate acid of our base. Okay? Any questions on this mechanism, this corrected mechanism? So one thing to note about this mechanism is that when we make these ethers, we are not touching the carbon-oxygen bond of the alcohol. So if we have the alpha anomer of our starting monosaccharide, as I've drawn here, we would get the alpha glycoside. If we had the beta anomer, we would get the beta glycoside. Of course, we always have a mixture of alpha and beta, but the individual alpha anomers will give the alpha glycosides, and the beta anomers would give the beta glycosides. Okay? And once we get the glycoside, there's no more interconversion. Remember, glycosides do not undergo mutarotation. Only the hemiacetal forms will undergo the mutarotation. Any questions? So we mentioned this again on Monday, but we'll mention it again. So we can take our polyether versions of our monosaccharides. And we can hydrolyze the ether at the anomeric carbon selectively. The book shows using aqueous acid. It actually needs to be either HCl or sulfuric acid, as we'll explain in a moment. Okay? But if we expose a glycoside to aqueous acid, such as HCl or sulfuric acid, we will cleave the acetal and convert it back into a hemiacetal. And we will get a mixture of anomers in this case, so I'm going to go ahead and draw the squiggly line, because now that we have a hemiacetal here, it will undergo mutarotation. So we learned the mechanism of this reaction on Monday, the hydrolysis of the acetal to give the hemiacetal. It's just the reverse of glycoside formation. But it will only hydrolyze the ether that's part of the acetal. This will not hydrolyze the ethers of the other alcohols in your monosaccharide. If you remember back to chapter 9, where we learned about ethers, we learned that ethers are less reactive than alcohols. Okay? So what happens when you react an alcohol with HX? What kind of product do you get? Alcohol plus HX. You get an alkyl halide, exactly. And so ethers, being cousins of alcohols, ethers can also react with HX to give alkyl halides. But because they are less reactive, you have to use either HBr or HI when you are reacting with ethers. So if you were to react a monosaccharide that had been converted into a polyether like this one with HBr or HI, you would convert all these ethers into alkyl halides. Usually we don't want to do that. Okay? So we're not going to cleave the ethers once we've made them on the alcohols, but we can cleave the ether that's part of the glycoside, but only if we use HCl or sulfuric acid, because these acids are not strong enough to react with the regular ethers. Okay? But HBr or HI would convert these regular ethers into alkyl halides. Any questions about this process? Selective cleavage of the acetal ether. So why would we want to make ethers from a monosaccharide? The answer is solubility properties. If we want to perform subsequent reactions in organic solvents, we would need our monosaccharide to be able to dissolve in an organic solvent. And we told you on Friday that they don't dissolve in organic solvents. They dissolve in water because of all the OH groups. So this is a way of making our monosaccharides soluble in organic solvents. And there's another way to do this. that is to make esters from our alcohol groups. Okay. So while I'm drawing this, I want you to think about the reagents we learned in chapter 22, I believe it was, for converting alcohols into esters. What can we react an alcohol with to generate an ester? And there's two of them, two choices. For references, yes?
Carboxylic acid.
Okay, you can use a carboxylic acid, and you would have to use a catalyst if you did that, right? An acid catalyst, and that's not as practical in this case. But what carboxylic acid derivatives could you react an alcohol with to get esters? Think of our most reactive carboxylic acid derivatives. Okay, acid chloride, very good. We use an acid chloride. So we could take acetyl chloride. And then what's our next most reactive derivative? An anhydride. Okay, so we could take acetyl chloride or acetic anhydride. We would need to use pyridine as a weak base to promote the proton transfers. And this would generate a polyester. I'm just going to write AC to abbreviate as acetate to save space on the structure. But this molecule is going to be a polyester. Many esters attached to all of our alcohols. Okay? And notice, like the esterification reaction, the esterification reaction retains the anomeric stereochemistry. Your beta anomer of your starting material, glucose in this case, would give the beta product. If you had an alpha, it would give alpha because you're not perturbing or breaking that carbon-oxygen bond at the anomeric carbon. Okay? This also serves as the same function as the esterification, generating more soluble carbohydrate derivatives that you could then dissolve in organic solvents. Okay? All right. Other reactions we can perform involve oxidations and reductions. We have a lot of functional groups in our monosaccharides that can be oxidized and reduced. And we will start with reduction. So in an aldose, the functional group that can be reduced is the aldehyde. So I'm going to go ahead and draw an aldose in the Fischer projection form. So we'll see the aldehyde. But of course, you could do this reduction on the cyclic hemiacetal, because anytime we have a cyclic hemiacetal, it's in equilibrium with a small amount of the open chain aldehyde. Okay? So we can take glucose and reduce it with sodium borohydride. And what we would get is a primary alcohol at C1. Okay. Okay. This molecule is known as glucitol, also called sorbitol. If you look at the ingredients on sugar-free gum, you'll often see sorbitol listed. It is a sweet molecule, but it is not a sugar, so it's metabolized differently than sugars. But it is sweet, so it's an artificial sweetener. It also helps preserve freshness and moisture, helps keep food products from drying out. So sorbitol is added to a lot of foods. In general, these alcohols that are derived from reduction of monosaccharides are known as alditols. Okay? So alditol is a general term for the reduction product you get from any aldose. And glucitol or sorbitol is the specific name that would be used by reduction of glucose. Okay? Questions? So we can also oxidize we have a lot of oxidizable functional groups in our monosaccharides. Let's focus on selective oxidations that are only going to oxidize certain functional groups, but not all the functional groups. So we've learned how to oxidize aldehydes to carboxylic acids. That was in, I think, chapter 20 maybe? So we learned it earlier on this year. What reagents did we learn for oxidizing aldehydes to carboxylic acids that don't oxidize alcohols? Anyone remember? We did a demonstration.
Silver oxide.
Okay, silver oxide, the Tollens reagent, which was silver oxide and ammonium hydroxide. Okay, so Tollens. There's some other ones. There's Benedict's reagent. There's Feeling's reagent. These are both copper-2 based species, copper-2 salts. And these are all nice because they give us nice color changes. I think Benedict's involves a red solution of some sort. But the problem with these is they're low yielding. They give us a nice color change, but they don't give us a very good yield of our aldehydes, or of our carboxylic acid. So if we want a better yield of our carboxylic acid, what we do is we use bromine and water. Okay? We're not going to go over the mechanism of this process, but we'll tell you that bromine can be reduced to bromide. And in that redox process, it is oxidizing its reaction partner. And so bromine is able to react with aldehydes and oxidize them to carboxylic acids. And you get a higher yield from that process. So if you're just trying to get a color change, or if you're just trying to use the reaction as an analytical tool to see whether or not you have an aldehyde present, then you would use one of these species. But if you're trying to get a good yield of the carboxylic acid, you would use bromine and water. Okay? And there is a general name for this species. This is called an aldonic acid. Okay? So much like the reduction product was called an alditol, this is called an aldonic acid. Any questions? So there's a vocabulary term associated with this process, and that is a reducing sugar. A reducing sugar is a sugar that can be oxidized by Tollens, Benedict's, or Feeling's reagents. Okay? Since these reagents only react with aldehydes, this reducing sugar is going to be a sugar that has an aldehyde or a hidden aldehyde. Okay? Notice that this definition is not the same as can it be oxidized in general. Okay? So we have an eye clicker question here. Let's go ahead and get our eye clickers out. And we've asked you which of the following sugar solutions, meaning if they were dissolved in water, can be oxidized. Okay? And this is oxidized in general. Okay? This is not oxidized by specific reagents, oxidized by anything. So go ahead and talk to your neighbors and answer this question, please.
Yeah. Like an awesome option. But only two of them are reducing sugar. You said oxidized in general, right?
Yes, this is oxidized in general.
Cool. Yeah. So A and B are reducing sugar, and C will turn into something that's not. I don't know. I don't know if it is. I could ask another question real quick.
All right, let's try to get these final answers in. Okay. More answers out there.
They could all be oxidized, but 1 and 2 are reducing sugar.
Okay, that looks like everything. Last chance. Okay, monosaccharide A, can we oxidize it?
Yeah.
Certainly. Monosaccharide B, can we oxidize it?
Yeah.
Yes. What about C?
I think so.
Yes, we have alcohols that can be oxidized, right? So indeed, we can oxidize it. The ketone, no, but the alcohols, yes. So all three of those sugars can be oxidized. But you'll note that this is not the same question as the following question we have, which is, which of the following are reducing sugars? Okay, this should be easy. I heard some discussion about this while you were answering the first question. So hopefully, oh, I forgot to open it, sorry. I do have to open it for you to answer. But it shouldn't take too long now that it's open to answer this question. All right, let's get those final answers in.
Yeah, it's just the same.
Three more answers here. Okay, almost there. Almost there. All right, there should be at least one more answer out there. Okay, I think we had 24 last time.
So these just
All right, we'll go ahead and stop that. Is A a reducing sugar?
yes.
Yes. Is B a reducing sugar?
Yeah.
Yes. Where's the aldehyde?
It is.
It's hidden. The hemiacetal is in equilibrium with the open chain aldehyde. Is C a reducing sugar?
No.
Nope, no aldehyde. Exactly. Very good. Okay. So now you are well versed on identifying reducing sugars. Your book has a figure showing this as well. And we notice that when we draw the cyclic forms of our sugars, if we have a hemiacetal and it's an aldose, then it's going to be reducing sugar, right? If it's a ketose, it won't. But an aldose drawn as a hemiacetal is a reducing sugar because that's in equilibrium with the open chain aldehyde, which can be oxidized. And notice that a glycoside is not a reducing sugar. Okay, the glycoside does not undergo the mutar rotation, not in equilibrium with open chain aldehydes, and therefore cannot be oxidized using Tollum's reagent or any of those relatives. Any questions on reducing sugars? Okay, so there's another way to oxidize monosaccharides that's also selective. But this one, instead of just reducing the aldehyde, it will or not just oxidizing the aldehyde, it will also oxidize the primary alcohol. So if we treat an aldose with nitric acid and water, it will oxidize the aldehyde to the carboxylic acid, just like bromine in water. But it will also oxidize the primary alcohol at C6, at the end of the chain, into a carboxylic acid. It will not oxidize the secondary alcohols. And the derivative of a monosaccharide that has carboxylic acids at each end of the chain is known as an alderic acid. Okay? So because we are transforming the functional groups at each end of the chain into the same functional group, the carboxylic acid, there is some stereochemical consequences to this reaction. So I'm going to draw allose for you. This is not one of the sugars you need to memorize the structure of, but it's going to illustrate something important for us. As I'm drawing the product we get from oxidation of allose, I'll mention that we're not going to learn the mechanism of this oxidation, but just suffice it to say that the nitrogen in nitric acid is at a very high oxidation state, so that nitrogen is getting reduced simultaneous to the oxidation of the aldehyde and the primary alcohol, but not secondary alcohols. Okay, so allose oxidized to its alderic acid. Is the alderic acid derived from allose chiral? No, it is not chiral. Why not? It has a plane of symmetry. That's one of the advantages of drawing the Fischer projection. Because it is an eclipsing conformation, it allows us to see whether or not we have a plane of symmetry. So there's a plane of symmetry in the alderic acid derived from allose, so it is a meso compound, achiral. All right, let's draw another monosaccharide, one we're more familiar with. We'll draw glucose. We're going to oxidize glucose with nitric acid and water. And as I draw it, as I draw the product, we'll ask you the question, is the alderic acid derived from glucose chiral? Okay, chiral? Yes, there's no plane of symmetry here. So, depending on the structure of the aldose you start with, you can obtain either a meso-alderic acid, which is achiral, or a chiral alderic acid. Okay. And so that's one of the advantages of drawing the Fischer projection. I told you that while it does not represent the real conformation, the Fischer projection is advantageous in certain cases because it allows us to see planes of symmetry when they're present. It allows us to see relationships in stereochemistry between monosaccharides. Any questions? All right, so now we're going to talk about a process that can be used to shorten the chain of a monosaccharide. So we can convert a hexose into a pentose or a pentose into a tetrose. And this is known as the Voll degradation. Voll was a German chemist. Much of this carbohydrate chemistry was worked out by Germans in the late 1800s. So this is shown with glucose here. And in step one, we're reacting glucose with this amine. It's a special amine. It's called hydroxylamine. It's giving us this compound called an oxime. Now, for a moment, let's just pretend that hydroxylamine is ammonia. What kind of a compound do we get when we react an aldehyde with ammonia in the presence of a mild acid? This is chapter 21 again. We're doing lots of review of 21 and 22 today. Aldehyde plus ammonia, or another primary amine. What would we get? We would get an imine, and an imine has a carbon-nitrogen double bond. We know the mechanism for how that forms. So an oxime is just a subset of imines. It's a special type of imine. It's an imine that has an OH attached to the nitrogen. So the OH group spectates in this first part of the reaction. It's just along for the ride. They should have written mild acid here. They're leaving out some details in this chapter. But this is just imine formation, going from an aldehyde to an oxime, a special type of imine. Okay? So then once we have our oxime, we're going to react that with acetic anhydride and sodium acetate. Okay? And there's two things going on in this reaction, so we're going to show that to you on the chalkboard. Okay? So we start out with our oxime. Okay, R is just the rest of our carbohydrate chain. We're just going to abbreviate it. We have our oxime. Our oxime has an OH group. What happens when you react an alcohol with an anhydride? We just talked about it. We erased it just now, but we had just talked about it. So hopefully we didn't just erase it from your memory. Alcohol plus anhydride. What do we get?
Ester.
We get an ester. So we're going to make an ester from that OH on our oxime. Okay? So this is called an oxime ester. And we have sodium acetate in there. That can serve the function of the pyridine, transferring the protons. We have a whole bunch of other OH groups that we could also convert into esters. But it turns out that the OH of an oxime, by virtue of being bonded to a nitrogen, is significantly more reactive, more nucleophilic than a regular OH. So if we just use one equivalent of our acetic anhydride, it will react selectively with the OH of the oxime and not touch any of our other alcohols. So we can get this compound by using one equivalent. But we're not done here. Okay, our sodium acetate is going to play another role. It can deprotonate this hydrogen, eliminating out acetate. Okay, so we've got acetate as the base, acetate as the leaving group. And then what is left when we eliminate acetate from that intermediate? We form a carbon-nitrogen triple bond. We've generated a nitrile. Okay? And because we formed a nitrile on a carbon bearing an OH group, that is called a cyanohydrin. Something we learned about either in chapter 20 or 21. I can't remember which right now. So. Okay, so two things are going on in step 2. We convert the oxime into an oxime ester. And then we eliminate out the acetate. That acetate attached to the nitrogen is a good leaving group. This is a fairly weak bond. And so we just do an E2 reaction to form a nitrile. And it's a special type of nitrile, a cyanohydrin. So I think that was chapter 21. So let's just say in chapter 21 we learned that if we treat a nitrile with a strong base, something happens. What is that? Does anyone remember? I'll start drawing it, and maybe it'll jog your memory, but so here is our cyanohydrin. Here's methoxide, our strong base. What's methoxide going to do when it reacts with a cyanohydrin? What's this strong base going to do? It'll deprotonate the OH. Now, of course, we have a whole ton of OHs we can deprotonate here, but there's only one bonded to a carbon that has a cyanide or a nitrile on it. Okay? So, when we deprotonate the OH attached as part of the cyanohydrin, we're going to eliminate out cyanide. Okay? So we lose cyanide. Cyanide is weakly basic. It's an anion on carbon, but it's weakly basic. So it's a reasonable leaving group. And what are we left with? An aldehyde. And then, of course, we form the conjugate acid of our base. Right? The methoxide gets converted to methanol. Okay? So in this particular step, we are cleaving a carbon-carbon bond. So what we've done in the course of the Vold degradation is we've converted the C1 aldehyde into a decent leaving group. We've turned it into a nitrile. When a nitrile is part of a cyanohydrin, it's a decent leaving group. So we can then deprotonate the OH of the cyanohydrin, eliminate out the nitrile, and so now we've turned C2, what was C2 in our hexose, into C1 of a pentose. And we've chopped off C1 and turned it into cyanide. Okay? So you can see here that we can convert glucose into arabinose. Is there another monosaccharide that would also give us arabinose when subjected to a Vold degradation? What was that? Mannose, yes. Why would mannose also give arabinose in this process? Yes?
So it's only different at the C2.
Yes, mannose and glucose are C2 epimers. C2 becomes C1 in the product. It's no longer a stereocenter. So it doesn't matter which of the C2 epimers you start with, you're going to get the same pentose in this case. So glucose and mannose will both give arabinose when subjected to the Vold degradation. All right, there is a companion process to the Vold degradation known as the Kiliani-Fisher synthesis that does the opposite. It can take a pentose and elongate the chain by one carbon, giving us a hexose. Okay, and it's a three-step process as well. Step 1 is just the reverse of step 3 in the Vold degradation. We take our pentose, treat it with sodium cyanide and HCl. In chapter 21, we learned that that makes a cyanohydrin. So whereas we're cleaving a cyanohydrin in the Vold degradation to break a carbon-carbon bond, we're generating a cyanohydrin in the Kiliani-Fisher synthesis to make a carbon-carbon bond and extend our chain by one carbon. In doing so, we've converted what was C1 of our pentose into C2 of this cyanohydrin, thereby generating a new stereocenter, and that will be formed as a mixture of epimers. That's why we have the squiggly lines here, indicating that that's a mixture of epimers. Step 2 employs a catalyst that is a cousin to the Lindlar catalyst. We learned last semester that the Lindlar catalyst will reduce alkynes to give cis alkenes. It's a poisoned catalyst, less reactive than palladium carbon. This palladium barium sulfate catalyst is also poisoned, so it will reduce the carbon-nitrogen triple bond of a nitrile, but not the carbon-nitrogen double bond of an imine. So that allows us to reduce this nitrile and stop at the imine. And then we know that when we treat imines with aqueous acid, we hydrolyze them to get aldehydes. Okay? So Kiliani-Fisher synthesis doing the opposite of the Vold degradation. We're adding a carbon to the chain as a nitrile, and then through these two steps, we're converting that nitrile into an aldehyde. So, if we start with arabinose, which we have in this case, which hexoses do we obtain from the Kiliani-Fisher synthesis of arabinose? We get glucose and mannose. We get a pair of C2 epimers. So whenever we perform a Kiliani-Fisher synthesis, we're going to get a pair of C2 epimers. And we know that glucose and mannose are such a pair. Any questions? So the Fisher in this case is Emil Fisher, who discovered a lot of things, also the Fisher esterification. But in the 1890s, he determined the structure of glucose. Right? In the 1890s, they had these monosaccharides. They knew they were different molecules. They knew they were isomers of each other because they had different melting points. They had different optical rotations. But they had no idea what their structures were. They only knew the molecular formula. They knew it was C6H12O6. They knew that it had an aldehyde and a whole bunch of alcohols. But they didn't know the actual stereochemistry. Emil Fischer figured it out with two analytical tools, a melting point apparatus and a polarimeter. It's a remarkable achievement for which he deservedly won the Nobel Prize, the second Nobel Prize ever given in 1902. So, to do this, to set the stage, first we have to look at these relationships. He also invented the Fischer projection, by the way. And so here we see aldopentoses and aldohexoses. He guessed at which enantiomers were naturally occurring. He guessed that the ones we call D were the naturally occurring enantiomers of sugars. So he was lucky and good at this, but that was the only guess. Everything else was brilliant deductive reasoning. So here we have D-aldopentoses. We don't have names because they did not know which structures matched with which names. So we're just calling them A through D and 1 through 8. But we have them organized here in terms of the pentose and the pair of C2 epimers of hexoses that you would get if you performed a Kiliani-Fischer synthesis on those pentoses. Okay? So, Fischer did the following experiments and made the following observations. So, the first thing he determined is that the Kiliani-Fischer synthesis, when done on arabinose, it yields glucose and mannose, and he identified them by measuring their melting points and optical rotations. So what could he conclude about the structures of glucose and mannose based on this observation? They're C2 epimers of each other. Okay? So he now knows that they're C2 epimers of each other. So they're one of these four pairs, but he doesn't know which one of those four pairs. Okay? So now he goes and performs another experiment. Okay? And that is that glucose and mannose both give optically active alderic acids. Okay? So you oxidize them with nitric acid and water. In both cases, the product is optically active. Does that rule out any of these pairs for being glucose and mannose? Okay, which ones have we ruled out? Can't be 1 and 2. 1 would give an optically inactive or a meso compound. Okay? So we now know, or Fischer now knew, that glucose and mannose were not 1 and 2. Any others? 7 and 8. 7 would also give us a meso compound. All right, so now he's chopped the number of possible structures in half. Let's see if we can keep going. Okay? So the third thing he does is he finds that when he takes arabinose, he finds that arabinose also gives an optically active alderic acid. Okay? All right, so does that rule out any more structures? Okay? Which ones do we rule out now? If arabinose gives an optically active alderic acid, which one could it not be? It couldn't be C, right? C would have a plane of symmetry right here. So 5 and 6 are not glucose and mannose. So now Fischer knows that glucose and mannose are 3 and 4, but he doesn't know which is which. He doesn't know if 3 is glucose and 4 is mannose or vice versa. So to solve that, he performs an ingenious experiment. He develops a way of switching the aldehyde and the primary alcohol. He develops a sequence of reactions, not a single reaction, but a sequence of reactions that converts the C1 aldehyde into a primary alcohol and the C6 alcohol into an aldehyde. He interchanges them. Because by looking closely at his Fischer projection, he realizes that there is an axis of symmetry in this particular structure, meaning if you rotate 180 degrees, you get the same compound. So that means if you switch the aldehyde and the alcohol on this molecule, you get the same compound back. In contrast, on this molecule, when you switch the aldehyde and the alcohol, you get different compounds. You rotate 180 degrees, these are different. Okay? So we found that when he applied this sequence to mannose, he got the same compound. So that means that 4 has to be mannose. When he applied that to glucose, he got a different compound. So that told him that glucose had to be 3. Okay? So this was an amazing use of logic and reasoning to unambiguously determine the structure of glucose. He actually didn't know which enantiomer was the naturally occurring one. He guessed on that, but again, he was lucky and very good at the same time. Any questions? All right, on Friday we will discuss disaccharides and polysaccharides and finish off the chapter.